Hello everybody! Today we are going to be wrapping up the equation derivation section of this course with the uncompetitive inhibitor derivation. First, let's do a short quick review of what uncompetitive inhibition is. Uncompetitive inhibition occurs when the inhibitor can only bind to the enzyme-substrate complex. Thus, the two complexes that can be formed during uncompetitive inhibition are the enzyme-substrate complex and the enzyme-substrate inhibitor complex. So let's start with the screencast. So this is going to be the screencast portion of the uncompetitive inhibition derivation. So the first thing we're going to be doing is initializing some of our assumptions, and the first is that the enzyme concentration change over time is going to be equal to 0. And we stated this because the enzyme concentration will not change as it undergoes the enzyme-substrate reaction. We're also going to be stating that the enzyme-substrate complex concentration change over time will be equal to 0, and that the enzyme-substrate inhibitor complex concentration change over time is going to be equal to 0. And this is because we're assuming the dynamic equilibrium. So, now what we're going to be doing to begin the derivation is we're going to be using the law of mass action to derive the enzyme-substrate complex change over time. So we're going to be stating that it's the rate of association, so the enzyme concentration times the substrate concentration times the K1 rate parameter, and we're going to be subtracting it from the rates of dissociation, which is the enzyme-substrate complex concentration times the K-1 rate parameter minus the enzyme-substrate complex concentration times the K2 rate parameter. We're then going to be finding the enzyme-substrate inhibitor complex concentration change over time, which is going to be equal to the rates of association, which is the enzyme-substrate complex concentration multiplied by the inhibitor complex concentration times the K3 rate parameter, minus the enzyme-substrate inhibitor complex concentration times the K-3 rate parameter. Finally, we're going to be deriving the product concentration change over time, which is going to be only the rate of association, which is the enzyme-substrate complex concentration times the K2 rate parameter. And finally, we'll be defining our enzyme total concentration equation for this equation. And we can see that there's going to be only 3 instances where we have the enzyme, and that's going to be the enzyme substrate complex, and the enzyme substrate inhibitor complex. So the total enzyme concentration is going to be equal to the enzyme concentration plus the enzyme substrate concentration plus the enzyme substrate inhibitor complex concentration. So now let's begin by taking the enzyme substrate complex concentration and making it equal to 0, and taking what we found as the enzyme substrate concentration complex concentration change over time using the law of mass action. And what this is going to mean is that our rate of association and our rate of dissociation of this complex are going to be equal to each other. And we've actually done this derivation many times before, but what we're going to be doing is dividing both sides by the substrate concentration times the K1 rate parameter. And this is because, again, we are trying to substitute for this equation, this total enzyme concentration here. We're going to try and substitute the enzyme concentration here with this equation. So what this is going to be equal is the enzyme substrate complex multiplied by the K-1 rate parameter plus the enzyme substrate complex times the K2 rate parameter over the substrate complex times the K1 rate parameter. And what this is going to mean is that the enzyme concentration is equal to the enzyme substrate complex concentration times the K1 rate parameter plus the K2 rate parameter, the K-1 rate parameter, over the substrate complex concentration times the K1 rate parameter. So this thus is going to be equal to the Michaelis constant. So now the enzyme concentration is going to be equal to the enzyme substrate complex concentration times the Michaelis constant over the substrate concentration. And what we're going to now be able to do is plug this right into this enzyme concentration here. So our equation is thus going to be the total enzyme concentration is equal to the enzyme substrate complex times the Michaelis constant over the substrate concentration plus the enzyme substrate complex concentration plus the enzyme substrate inhibitor complex concentration. So now what we're going to try and do is find this in terms of the enzyme substrate complex. So what we're going to be doing is we're going to be taking this equation that we derived for the change in the enzyme substrate inhibitor complex over time, and we're going to be making this equal to 0 due to our assumption of dynamic equilibrium. So it's going to be the enzyme substrate complex times the inhibitor complex times the K3 parameter equals the enzyme substrate inhibitor complex concentration times the K-3 rate parameter. And what we can do, because we're trying to make this in terms of the ES value, is all we have to do is divide this, both sides, by K-3. And what we're going to find is this right here is going to be equal to 1 over Ki. So the enzyme substrate inhibitor complex concentration is going to be equal to the enzyme substrate complex concentration times the inhibitor concentration over the inhibitor constant. So now we can take this equation and plug it back into here. And what we're going to find, or actually we should plug it back into this equation because this has the updated E value. So what we're going to find is our total enzyme concentration is going to be equal to the enzyme substrate complex times the Michaelis constant over the substrate concentration plus the enzyme substrate complex concentration plus the enzyme substrate complex concentration times the inhibitor concentration over the inhibitor constant. So now that we have this equation, we can isolate the enzyme substrate complex because, again, our goal is to plug this back in to our product concentration change over time, which is the enzyme substrate complex concentration times the K2 rate parameter. And to do this, we're going to first isolate the enzyme substrate complex concentration so that it's going to be this value right here. And what we're going to then do is divide both sides by this value. So it's going to be equal to the enzyme substrate complex concentration is equal to the enzyme total concentration, or the total enzyme concentration, over the Michaelis constant over the substrate concentration plus 1 plus the inhibitor concentration over the inhibitor constant. So we can now take this equation and plug it in to this ES in the rate of product concentration change over time. So dP dt is going to be equal to the total enzyme concentration times the K2 rate parameter, which we can simplify to make the Vmax value, over the Michaelis constant plus over the substrate concentration plus 1 plus the inhibitor concentration over the inhibitor constant. So what we can do to get this into the official format is multiply both the numerator and the denominator by the substrate concentration. So we're just going to have the Vmax times the substrate concentration equals the Michaelis constant plus the substrate concentration plus the substrate concentration over multiplied by the inhibitor concentration over the inhibitor constant. And then we can finally isolate the substrate concentration within the denominator. And this is going to be our final equation. So, thank you very much for watching this video, and I hope this was helpful for you to learn the uncompetitive derivation.